So in this video, I'm going to explain the next arithmetic instruction as a INX. So here the function of IN means it is here increment and the X means register pair. So overall the function of this instruction is increment register pair by 1. So first of all we'll see their opcode of this instruction is INX and their operand will be register pair. So this register pair should be taken as a BC register pair. It is denoted by B. So here we should write B. Then DE register pair is written by D. So this can be denoted by D. Then HL register pair is denoted by H. And after this SP. So here there are another register pair also which is called as a PSW, program status word, so in which their higher byte is accumulator and lower byte is called as a flag. But this register pair is not used here. This register pair as a PSW is not used here along with this increment. This instruction as INX. So if somewhere it has written INX PSW, it means it is invalid instruction with respect to 8085 microprocessor. So during the exam they might be asking these kind of things also. So here our attention must be there, what are the register pair used along with this instruction. So register pair strictly used are BC register pair which is denoted by B, DE register pair which is denoted by D, HL register pair which is denoted by H, and stack pointer which is in the short form denoted by SP. So these four register pairs only used here along with this instruction as a INX. So let's see for example how we can understand this. This we can write as a INXH. So basically this instruction is used whenever we are performing the memory related operation or stack related operation. So when we need to move or address large scale of the memory, then by that time as a memory pointer we are using this instruction to increment one by one and point to the addresses or point to the memory location by that way. So here for example what this will perform the operation. So what is the content of HL? It will be incremented by 1 and then after incrementing it will be updating or it will be storing the result into the same register pair here. So let's say before execution of this instruction, if we are considering this HL content as this HL content, we are assuming that this as a 0 triple FH. So here this HL register pair is in HL. This is having 0F. This is having FFH. So H is individual 8-bit, L is individual 8-bit, but combinedly as a register pair, this number is treated as 16-bit number. This HL content is treated here as a 16-bit number. So here this instruction will perform 16-bit addition. So here how it will be? First of all we could write this HL as a 0 triple FH in terms of binary. So how to write this? This will be 0 0 0 0. Then this FFF can be written here 1 1 1 1. Then again 1 1 1 1. Again 1 1 1. So this is 0 triple FH. It is the content of HL register pair here. Now it should be incremented by 1. It means in this one we need to add 1. So 0 0 0 1 H. So in this form it can be written 0 0 0 0 0 0 0 0 0 0 0 0 and here 0 0 0 1. So now you need to perform the addition of this. So 1 plus 1 sum will be 0 and carry will be 1. So again 1 plus 1 plus 0 sum will be 0, carry will be 1. Like that it will be here 0, 1, 0, then again 1. So these bits also will have 0, then again here 0, again here 1, this is 0, this is 1, this is 0, and again this will be coming here as a 1. So 1 plus 1 plus 0, it will be 0, then carry will be 1. So 1 plus 1 plus 0, sum will be 0, carry will be 1. So 1 plus 1 plus 0, sum will be 0, carry will be 1. So 1 plus 1 plus 0, sum will be 0 and carry will be 1, and at this stage 1 0 0, it will be 1 here, and remaining bits it will be 0 0 0. So like that, in the form of hex digit, this can be written here as a 1, this is here 0, this is here 0, this is here 0. So this HL, whatever we have it here as a 0 triple FH, if 0 1 is added here as like this, then this will become here as a 1 triple 0 H. So this is the result will be stored after execution of this instruction. So after execution of this instruction, if you check it here, the content of HL, then this will be here 1 0, this will be 0 0. So this will be the result after execution of this instruction. So now we'll see that rest of the part as a size, machine cycle, T states. So size here, as like if we are writing INX H, then in this instruction if you see that this is having only English alphabet. So based on that logic, here size in terms of byte, it will be only 1 byte. It means it is required only one memory location to store the opcode corresponding to this INX H. Now, what about the machine cycle? So here, this will take only one machine cycle because corresponding to this INX H, there will be code which will be stored into the memory before execution of this instruction. So that code will be fetched from memory to the processor, and that is called one machine cycle as a by default opcode fetch machine cycle. So machine cycle will be only one here. Now rest of all the things, as like the content of HL is this register pair, as a HL is inside the processor, so their content should be added by this one. So this adder and this all the things is available inside the processor itself. This arithmetical logical unit and these operands, these all are available inside the processor only. So outside from the processor, it is going to fetch only opcode. So it means it is going to access this memory chip only once. So that is the reason it is having only one machine cycle. But T states here, it will be changed. How it will be? The number of T states required here, it will be 6. So compared to INR, if we compare INR and INX, in INR, we need to perform only 8-bit addition operation. Here, it is performing 16-bit of the addition operation. So during the execution time, this time will be taking, this will take somewhat more time. So that is the reason 2 extra T state is required to complete this addition operation of 16-bit. So that is the reason T states required for this INX is 6 T state. Otherwise, every time I told that by default the T states for the opcode fetch is 4 T state. But wherever it is somewhat operation is different from the normal operation, then this T states will be changed for this opcode fetch. So opcode fetch will have only 2 values. By default 4 T state, and few of the instructions will have 6 T states. So how many instructions will have 6 T state for the opcode fetch operation? That list I'll give you by the end of this instruction set itself. So in that way you must have to remember that data also. Now we'll talk about the flags. So here the key point in this is flags status. Here how it will be, no flags are affected. No flags are affected. no flags are affected by the execution of this instruction as a INX means what? What are the status of the flags before execution of this INX? It will not altered. It will be as it is. So here no flags are affected by the execution of this instruction INX. That is the key point here. This is the key point you must have to remember. And the another key point is here the number of test states required for this instruction for opcode fetch is 6 test state. So these 2 points are very important here. And third one is you must have to focus on this. What are the register pairs used? Otherwise already I had given if they'll give something as like PSW as a register pair, that is not valid for this instruction. So here we have to remember like that, and these instructions basically used to use as a memory pointer during the execution of the stack related program or memory related program. So that is the reason it is not performing any arithmetic operations apart from this addition which is used to point to the next location. So here if it is currently at 0 triple FH, now if this INX H will be executed, it means now the HL pointer will point to this memory location. So one by one it is going to point to the next level of the memory location or memory address. So that is the reason it is used as a pointer itself. So due to that reason no flags are affected here. And why it is required 6 test states, that already I had explained, because it is going to perform 16 bit of addition to make it here as an increment of the register pair content by 1. So this data already we had seen before execution, and this is the data of the HL after the execution. I hope you understand this instruction with much of clarity in the better way. Thank you.